Welcome. Welcome to week 4 MSI Advanced Topics in Plane Geometry. So today we are going to talk about Erdos model inequality. This is a very classical and important quality. And the reason I pick up this topic is because number one, of course, this is a famous inequality and a famous property in Euclidean geometry. Number two, this theorem, this inequality, is a typical example how people can use algebraic method in Euclidean geometry. Even because of these two reasons, and it is worth for me to pick up this topic, introduce this topic to you. But there's a even more important reason for me to generalize this inequality. And there are a lot of open problems. If you are interested, you can talk to me further, or you can investigate, you can do research by yourself. It is actually related to the generalized Amgm inequalities. And what is Amgm inequality? Amgm inequality in its prototype is a squared plus b squared is bigger than or equal to 2ab, and the equality is true if and only if a is equal to b. The Amgm inequality plays one of the central roles in mathematics. Inequalities are very, very important in calculus and in partial differential equations, for in everything you will learn in the future. Okay, so some familiarity with the Amgm inequality would be very useful. Okay, so let's go back to Erdos model inequality. Paul Erdos is a very famous mathematician. He is a Hungarian mathematician. And in 1935, he posed a problem in the American Mathematical Monthly, the following question. So let ABC be any triangle, and let P be any point inside the triangle. Then the distance of P to A plus P to B plus P to C, which is the distance, the summation of the distance from P to the three vertices, is at least twice as the summation of distance of P to the three sides, P to the D, P to the E, and the P to the F. So this is the inequality. And so 2 years later, the problem was solved by L.J. Model and D.F. Barrow. And so the method is one of the simplest methods. After that, there were, I guess, more than 100 different proofs of this famous inequality. And so this inequality should have been called the Erdos model Barrow inequality. So I don't know why Barrow was forgotten. Anyway, so nowadays people call this inequality Erdos model inequality. So I will provide 3 different proofs of this inequality. Each of them are very, very important, and you should digest the method. These methods are very useful, and they are important methods in geometry. The first one, we will use the law of sines and the law of cosines. We will use some trigonometry. And the proof is the simplest by using trigonometry. All right, so remember the inequality is PA plus PB plus PC is greater than or equal to PD plus PE plus PF, 2 times that. Okay, so it requires some computation. So here is the picture, and we just pick part of the picture to the right-hand side. So this is part of here. And we study the relationship among them. So after all, here in this picture, X, Y, and C are in the inequality. In fact, so if I use, this is called A, this is called B, this is C, and this is called X, this is Y, this is Z. By the way, in a triangle, we always label things in a systematical way. Triangle ABC. And so so the first angle is, of course, angle A. The second angle is angle B. The third angle is angle C. What is, in our convention, the first line, the first side? It's not AB. It's actually BC, because the opposite angle of BC is angle A. Okay, and so then CA, because its opposite angle is B, and then AB. So in that order. So usually the distance, we name the distance P to the A to be A, and then P to the B to be B, and the P to the C to be C. That's fine. But then the distance of P to the BC, we usually name it as X. And the distance of P to the CA, Y. Distance P to the AB, Z. Okay, so in that way, we can write the inequalities, write the expressions in a more symmetric and a systematical way. Okay, so this is a little trick. And so if you, as I said, if you grab this small piece of the picture to the right-hand side, you said this picture is very useful and interesting, because the Erdos model inequality is A plus B plus C is bigger than 2 times X plus Y plus Z. So in this small picture, there are at least 3 relevant values there, X, Y, and C. Moreover, we have 2 right angles. And so therefore, there's a relationship between X, Y, and C, which we are going to explore. So we know that since we have these 2 right angles, these 4 points are so-called concyclic, right? There's a circle that passing through all these 4 points. And so let's compute using the law of cosine, the side ED. Okay, first. So by law of cosine, so ED would be, so this is angle C. And so this would be angle pi minus C, 180 degrees minus C. So keep that in mind. We would know that ED square is equal to x squared plus y squared minus 2xy cosine of this angle. And so this angle is pi minus C, 180 degrees minus C, which turns out to be AB. Okay, so ED square is this guy minus 2 cosine AB. But we know that by trigonometry, cosine of A plus B is equal to cosine of A, cosine of B minus sine of A, sine of B. That's trigonometric inequality. And if we put this inequality in, something magic happens. Okay, so we can actually write this ED square as the square 2 squares, basically. And so this is called, there's a name for this, Lagrange method of completing square. This is the way to prove that, well, you don't have to prove that ED square is positive because it's all non-negative, because it's always non-negative. But I would like to see a way to write something into the sum of 2 squares. In this particular example, if I expanding cosine A plus B using this identity, we can actually write ED square in terms of these 2. Okay, I can write that in terms of that too. And so, of course, this is the trick. I can ignore one of them. This I can get rid of them. This is positive. So what I would see is that ED square would have been bigger than this guy, bigger than or equal to, and take square roots on both sides. I get my inequality. ED is actually equal to x sine of B plus y sine of C. So this is an inequality which you cannot, I'm not saying you cannot prove. It's not easy to see from the geometric point of view. It's purely from algebra, because you use law of cosine. ED is something related to cosine of C. But it is only through trigonometric identities. So cosine of C is somehow related to trigonometry functions of A and B. And this is a purely algebraic procedure which would let you prove ED is bigger than these 2, which is obviously nice because number one, x and y are something is included in the inequality. Sine A, sine B, of course, these are the data. These are in the given inequality. And of course, ED is not what we wanted. This is it's not something in the Erdos model inequality, but we can compute ED in another way using law of sine. Here we would use the fact that the 4 points CE, PD are concyclic. And not only CE, PD are concyclic, but also CP, that line, happens to be the diameter of the circle that passing the 4 points of CE, PD. Okay? And then by law of sine, we know that ED is actually equal to C, which is the length of CP, times sine C. Wow, this is very nice. And so therefore, we actually would get, by dividing sine C on both sides of the above inequality, I would get C is bigger than or equal to x times sine B, and y times sine B over sine C, and y plus y times sine A over sine C. Okay, so that's the fundamental inequality, sorry. That's the fundamental inequality we obtained, the fundamental inequality. Okay, so that's what we have. And so next thing is we can do the same thing for the other 3 parts. And so if we do that, we would get other 2 inequalities. I can write them explicitly using the same method. So A is greater than these 2 guys, and the B is greater than these 2 guys. Okay, and so therefore we have A plus B plus C would be basically adding up the right-hand side we obtained. So each right-hand side contains 2 terms, so put them together, we have 6 terms, and we factorize the common fact, we would get these 3 terms. And then you observed that these 2 numbers are reciprocal to each other. So then we would use the arithmetic and the geometric inequality I mentioned at the beginning of the class. So basically this said x plus 1 over x. If x is a non-negative number, then we would have that x plus 1 over x is bigger than the square root of x times 1 over x, which happens to be equal to 2. Okay, so these numbers, these expressions are all bigger than or equal to 2. And then we get the inequality. So that's using the trigonometry that gives us the quickest way to prove it. Okay, so let me review the proof, because this is not only this method I think you should memorize. I memorized this for 40 years, I would guess. When I was a kid, I knew that proof. For 2 good reasons. Okay, so number 1 reason is that we use trigonometry, we simplify the proof, we use inequality, we simplify the proof. That's number 1. And number 2, which is probably more important, you probably observed that we simplified our proof by saying that we first prove, we separate the question. So we chop the question into 3 small pieces. And for each piece, I studied this carefully, and I would get the inequality, which is the inequality here. I said the fundamental inequality. And once you set up this inequality, you prove a inequality by yourself. You prove the theorem by yourself. Okay, and then you can use this 3 times, actually in another 2 times. Okay, so then you amplified your power, basically. Okay, you don't prove some things from very beginning to the very end. You just prove we call it in mathematics, we proved some small lemma. And this small lemma you can use many times, and you can get a lot of results. You can generate a lot of results and put these results together, and then we prove the theory. Okay, so this is a math idea or math trick is that if you have a big complicated problem, you always want to chop it small and study the small question, study a smaller question, and set up some inequality, set up some results for the small part, and then use it many times. Use it in different ways, in different occasions, and then put them together. You probably can solve a big and difficult problem. All right. So this is the first proof. Let me go to the second proof. The second proof is in spirit the same proof as in the first one, but it contains a very nice trick. Okay, so number one, it looks like it's more elementary. Okay, it does not require us to know trigonometry, but using the area method. But it includes a very nice trick that you should also think about this very carefully. Area method. Okay, so I would say this is not the easiest proof. The above proof is the easiest proof. The second proof is not the easiest, but certainly it is the most elementary. We of course we will use Amgm inequality, but in terms of geometry, we will only use area method, just using the area. Okay, again, we will assume P equals A, PB equals B, PC equals C, and X, Y, Z are set up in the usual way. And the one observation is that we will use, which one we will use? Take R. Okay, so as I said, then we want to name the side lengths of the three sides of the, and so the length of the three sides of the triangle. So usually we will use ABC, but since we have already used, ABC has been used up, we will use another three letters to denote the length of the triangle. So I will use PQR. So as you can see that I will name the length of BC to be P, because BC in my mind is the first side, and the CA is equal to Q and the AB is equal to R. And by area consideration, we will have the following inequality. So this R, which is here, this is R, and so this is A, and this is X. Okay, and did I do anything wrong? I should maybe R. Okay, so this is, okay, sorry, this is R, PQR. R, this is P. I'm confused myself. Okay, so R, and this is A, this is C. Okay, so this is C, and this would be PQ, PF, which is Z, right? And this is A, this would be B, and okay, so that's enough. No, this X, Y. So the right-hand side, you would see Q times Y. So this is R, this is P, this is Q. Q times Y would be equal to twice the triangle PAC area. And the P times X would be triangle PBC, And the other one will be 2 times the triangle PAB. Okay, I prefer to write this as triangle PCA. Anyway, so this will add up to the area 2 times of the triangle of ABC. So the right-hand side is the 2 times the triangle of ABC. Let's see the left-hand side. Left-hand side start with R and C plus Z. And we will see that the C plus Z will always be bigger than or equal to the height. Because height is the shortest distance go from C to AB, and if you go from C to P and P to F, that's a broken line which should be longer. Okay, so this tells us that the C plus Z would be bigger than H. So therefore, R times C plus Z would be bigger than equal to R times H. But what is R times H? That's also 2 times the triangle area, ABC. So we set up a very nice inequality, which I would say by the area consideration, it is equal to that. Okay, and so you can simplify this to get the inequality R times C, RC is bigger than QY plus PX. Okay, so that's a nice, very simple inequality, and you obtain it just by area considerations, then you get it. Okay, so you may think by using, I have experience of the above one, so I would say C is bigger than Q over RY bigger plus P over RX. You probably think, okay, I can use this and run this in 3 times to the other 3 corners, and so add up, and I will get Erdos model inequality. It turns out this is not true. Okay, you can try it, and you can also compare this to the inequality here. Maybe I can compare it. So what is Q over R? Q is here over R. By law of sine, this is sine B over sine C y plus P over R. P over R is sine A over sine CX. And you compare this to the fundamental inequality here. You see they are very similar, but they're different. Okay? It just tells you that both inequality must be true. Okay, but this is useful, this is not useful. You can try it. You run this 3 times, you add them up. You cannot use Amgm inequality, I'm sure you. Okay, here's the trick. I will claim if this is true, then this must be true. Okay, and here is the trick. So the above inequality, which let me erase all the unnecessary markups. So this inequality is actually true for any point P, not just for one point P. So for any point P in the cone of triangle of this angle, right? So you do the same thing, everything, you repeat it, you will see that this is the case. And this is true even let's say P is here. It's in the cone of this triangle, but still, it may be outside the triangle, but still in the cone. So now what I want to do is I can fix this C, and what I do is I just basically switch in. This is X, this is Y. I can switch X, Y. So what I want to do is I pick up the P fixed that I just let A goes here and the B goes there. So this is called A prime and B prime. So basically I flip the triangle ACB, but without flipping the angle. The angle itself won't change, but the A becomes A prime, B becomes B prime. So if I run this, what I will get is not RC is bigger than QY plus PX, because Y and X won't change, but Q is this, and the P is that. But we're switching P and Q. Okay, so that's the trick, because this is true for any point P inside the angle ACB. So I can flip it. And so since this is always true for P and Q, what I really would prove is R bigger than C is Q, making Q to be P. So it's PY plus QX. And that's the magic. Okay, so from this inequality, I can actually switch in P and Q and get the second inequality. And this second inequality will solve our problem, because so now if you say the P is bigger than RY plus Q over RX, so we can compare this inequality with the fundamental inequality. For the fundamental inequality in the denominator, they are always sine C. And for the X one, this should have been sine B, but we have a Q. Q is the second side, which the opposite angle is sine B. So you exactly have the sine B here. And so which with respect to Y is sine A, which is corresponding to P. Okay, so you see, this inequality is the same as this, except that in the first place, we use trigonometry to prove it directly, and in the second place, we use area consideration, but we flip the two sides. So we use the fact that it doesn't matter the length of P and Q. You can actually, okay, in the lecture notes, I said I can vary P and Q. I actually fixed vary X and Y. I can, in this, I actually fixed X and Y, but I vary P and Q. And it's still true. All right. Okay. So that's the nice part of inequality. So this Z depends on, when you flip it, it will change. The problem is that this is cancelled. This Z is cancelled. Here you have it has nothing to do with Z. So therefore, you will get your answer. Okay, so once you get this inequality, which is the same as the fundamental inequality, we use Amgm inequality, we are able to prove the Erdos model inequality again. So this is the second proof. It's the most elementary and the best, the trickiest way. It's a nice trick. Okay, it's difficult, but it's the nice trick. The third way, which is the way I'm going to generalize it to the place that you will learn a lot of new types of Amgm inequalities, which will be very, very useful to your future. Okay, so we will use purely using algebra. What's the spirit of algebra? Computing out, write out everything in terms of algebraic expression, and then do it. All right, so we let PA equals A, PB equals B, and PC equals C, X, Y, Z, everything. And so we assume that BPC, so this would be the first angle because it's BC, and let this be beta, this would be gamma. And okay, I use this to be 2 alpha, 2 beta, 2 gamma, that's fine. And we note that 2 alpha plus 2 beta plus 2 gamma is equal to 180 degrees. And so therefore, just remember, which we'll use very often, alpha beta plus gamma is equal to 180 degrees. The inequality this time I needed is the inequality between, so this is Z, and this is AB. Okay, I claim that Z is less than equal to square root AB times cosine gamma. Well, this is another algebraic geometric inequality, which by itself is useful. So how to do it? So there are many ways. So the classical way is that you can do a angle bisector called CF prime. And of course, Z is less than PF prime, and there's a formula for the length of angle bisector, which you can prove that this is less than square root AB cosine C. But here I would use the law of cosine to do it again, using the law of cosine. So this length AB is equal to R. So by law of cosine, R squared is A squared plus B squared minus 2AB cosine 2 gamma. This is the angle 2 gamma. And so I complete the square using this strange way, A minus B squared plus 2AB. And then I drop this, I throw it away. So this is bigger than 1 minus 2AB. And so by double angle formula, this would be 4AB sine square gamma. And then we are done, right? So, okay, not done, but we use triangle. So we know that R times Z, what is R times Z? R times Z is again twice of the area of PAB. But we have the formula for triangle area, so as triangle PAB, that's half of AB sine 2 gamma, right? Half of AB times sine of the angle they make. And so therefore, RZ is equal to that. So I can essentially divide it R here. So this equality is just by area consideration. All right, so, but then R squared is bigger than that, so I substitute R squared bigger than that but then R is in the denominator, so the inequality is less than or equal to. So you put this information in, and using the double angle formula again, you would get the z is less than square root AB times cosine gamma. As I said, this is by itself a nice in upper bound estimate of the height of a triangle. The height of a triangle is always less than square root AB times cosine of that angle, half of the angle. Anyway, so then I will actually prove a more generalized version of Erdos model inequality. I will prove this inequality. I will prove this inequality. Okay, so this is an inequality which, you know, this each one is bigger than 2z, 2y, 2x, and you are done. Okay, so from now on, so this algebraic inequality is just jump out of the geometry. You know that in Erdos model setting, ABC, if ABC is a three sides of a triangle, then you would have A plus B bigger than C, C plus A bigger than triangle inequality. But we are going to prove a inequality which I called generalized Amgm inequality, which is just for any ABC, this would be true. Of course, here we require ABC to be non-negative real numbers. Okay, so this is exactly what I want to prove. But then, since ABC are non-negative numbers, I can always rewrite A as A square, some number square, B as B square, C as C square. So the left-hand side is A square plus B square, C square. The right-hand side, nicely, you can get rid of the square root. So it's 2 AB cosine gamma, 2BC cosine alpha, 2CA cosine beta. Okay, so that's the inequality we want to prove. And I call the generalized Amgm inequality because you have the freedom to choose different angles, alpha, beta, and gamma. For example, if you choose alpha and beta to be of 90 degrees, and the gamma to be 0, so then they add up to be equal to 180 degrees, you will see that, well, cosine 90 degrees are zeros, so these two goes away, but cosine gamma is equal to 1. And so this inequality will reduce to A squared plus B squared plus C squared is bigger than 2AB. But then you can take, because C is arbitrary, you can take C to be 0 to get the usual prototype version of arithmetic and geometric inequality, number 1. But I can choose alpha, beta, gamma to be equal. And in this sense, I choose alpha, beta, gamma to be equal to 60 degrees so that they add up to be equal to 180 degrees. And then I get an inequality called A squared plus B squared plus C squared is bigger than AB plus BC plus CA. This is an interesting inequality because this is a inequality, arithmetic geometric inequality regarding to 3 numbers. And so it's interesting because then the coefficients is not true anymore. You can easily see if you write 2 here, the inequality is not true for general ABC. So it's surprising because it was surprising because for 2 numbers the coefficient is 2. For 3 numbers the coefficient is equal to 1. Okay, you can play the same game to investigate for high numbers, for A squared plus B squared plus C squared plus D squared, what would be the optimal coefficient? It has to be less than 1. Anyway. Okay, so this is the inequality, and you can also go to the other extreme. Alpha, beta equals 0, gamma equals 180 degrees. Then the inequality becomes this. Well, you do have 2, but you have to allow one mixed term to be negative 2. Okay, if all of them are positive, the inequality is not true. Okay, so because of the freedom, I call this generalized Amgm inequality. In a lot of cases, this would be very, very useful. Okay, looks like it's a horrible inequality to prove. And here, I will give the so-called Lagrange completing square method to prove it. Okay, and so here is the proof. essentially, we will make use of the assumption that alpha plus beta plus gamma equal to 180 degrees. And so then I basically, using the same method, I expand, rewrite cosine gamma in terms of negative cosine alpha plus beta, and so then I expand it. So the inequality will be the inequality with regarding A, B, C, and alpha, beta, and then there's no constraint for alpha and beta because I don't require alpha, beta to be positive, negative, more than 180 degrees, and so on. So then this inequality becomes to prove that this is non-negative, and here is the perfect way called the Lagrange Lagrange method of completing squares, and by a simple computation, you would see that you can write this complicated expression in terms of these two, and then you are done. Okay, so I strongly urge you to do the computation by yourself to get the flavor out of how to find this completing the square, writing this as the square sum of the square of two quantities. And so this is actually one of a good method to prove inequalities. So if you want to prove something is non-negative, well, the easiest way is to write that guy in terms of sum of squares, and therefore it is negative. Okay, so from this you can also seek the question to find conditions where the equality would be true, and the equality would be true is if and only if both of them are equal to 0, and then you will get some relations, right? So B sine alpha minus A sine beta equals 0, and the B cosine alpha minus A cosine beta is equal to C. And you can actually solve B's A in terms of C. And that will give you the case, you can identify the case of, so under what case A, B, C would the equality would be true. Okay, so I will put this as one of the exercises problem. All right. The next one is a surprising method. I learned a lot from this method. I was truly surprised by the method. Okay, so remember we want to prove the Erdos model inequality. So this is what we want to prove. And what we have done is that we successfully turned this algebraic geometry question into the algebraic inequality. Okay, and through this procedure, we actually make some abstractions. So the original inequality actually is this. And then I said I can, because A is a non-negative number, I can write A as A1 square, B as B1 square, C as C1 square, and then we have the inequality like this. And so this second method is actually, I just turn this algebraic inequality back to a geometry question. Okay, and so what I have done is that I draw the following picture, which is basically irrelevant to the original original picture of Erdos model inequality. Okay, so I just turn the algebraic question back to geometry, but this time with a different picture. Well, since you say alpha plus beta plus gamma is equal to 180 degrees, I can actually draw this picture making, okay, so I'm making this to be A, and this to be negative A, which I can do that. And so then I can rotate from A counterclockwise, say by the angle of gamma, and I can define Y. So I want y1 square plus y2 square is equal to b square. I want this length to be b and this length to be c. Okay, so basically I start from x equals a0 and I rotate the gamma angle, and with length b I get y, and starting from y I just rotate counterclockwise by beta and I get z. Okay, and this length is called C. So now let's interpret this geometry picture. So the left hand side is equal to a squared plus b squared plus c squared. I don't do anything. But the right hand side is interesting. So what is AB cosine gamma? Right? We have three terms: AB cosine gamma, CA cosine beta, and AB cosine alpha. So let's figure out AB cosine gamma is. Let's say BC cosine beta, let's say. BC cosine beta, I can use law of sine, law of cosine again. So that would be, this would be equal to half of b squared c squared, and this length would be equal to this guy, right? In this triangle, right? So this is b, this is c, this is something whose square is this, because we have coordinates, right? And so this is law of cosines. And so then I expand it, I will get b squared plus c squared minus y1 squared minus z1 squared minus y2 squared minus z2 squared plus 2y1 z1 plus 2y2 z2. Why this is useful? Because I said y1 squared, y2 squared, this length is b. So you know that these two together cancels with b. And you will see that the c squared cancels with this. So everything cancels with everything. You are left with a very nice expression, y1 z1 plus y2 z2. So that's for BC cosine beta. And if you use the law of cosines again for the other two triangles, you would get AB cosine gamma is AY1, and the other one is negative AZ1. Okay, so now putting them together, the trigonometry goes away. You want to prove that this guy is going to be equal to the right hand side. Of course, that's through a lot of some computation you want to prove this. But the nice part is that you can separate the problems into two. So I have a squared here, y1 squared, z1 squared. And you just need to take care of this term, this term, this term. Okay, so what I want to prove, a squared plus y1 squared plus z1 squared is bigger than negative 2az1 plus 2ay1 plus 2y1z1. And that inequality, we just proved this, right? We have coefficient 2 with 1 negative. You can complete the square like this. And the other two you can prove by the other. y1 squared plus z1 squared, obviously, by the Amgm, which is obviously bigger than 2y2z2. So you split this complicated one. Using geometry picture, you get rid of trigonometry. And also you split this complicated inequality into two inequalities which are separated and easy to prove. Okay, so that's a nice one. So I said this is interesting because not only it works in this situation, but also it works in much more complicated situation. So you may ask yourself, in any triangle, inside the triangle, inside a point inside the triangle, the distance of three sides, the sum of distance to three sides is at least twice as the distance of three sides. Three vertices is at least twice as the three sides. How about if I have a convex polygon, and if I have a point P inside it, and the sum of distance of the three vertices comparing to the sum of the distance of all n sides, not to all the vertices, to all the three sides. And what would be the optimal inequality? And if you check this for regular polygon, and you take P in the center of the regular polygon, you can actually compute. Okay, so the distance and the side, they have a relationship, right? So let me draw the picture. So you have, I draw a hexagon, okay, and the summation to all the all the six vertices is, let's say, R. and there are 6 of them. And the summation, the distance to all 3 sides, well, it depends on this angle. This angle is pi over 6. Why? Because this is pi over 2 pi over 6, which is 60 degrees. And then half of it is pi over 6. In general, if you have a regular n polygon, this would be pi over n. So the relationship is basically, so this is h. So r is bigger than how many h? Secant pi over nh. Okay, so this number, this secant pi over n is obtained when you assume that the polygon is a regular polygon and the p happens to be in the center of this regular polygon. So can I make a conjecture that in general, this is true? Well, this is not a conjecture anymore. This was proved by Lenhard, that if A1 through AN, these are the vertices, A1, A2, AN, to be a convex polygon and P is an interior point of that. And let Ri be the distance from P to the vertices AI, and the little ri be the distance of P to each sides. And then the left-hand side is the summation of the distance to all the vertices. Then the right-hand side is the summation for all the n sides, and they are related. The inequalities, they are bigger than the secant pi over n. So you can imagine this would be a very difficult problem to prove using geometry or algebra anyway. So I will use the third method I proved before and turn this inequality in a purely algebraic inequality. So this time I will use the fact that, so alpha I summation is equal to 180 degrees, not 3 of them, summation to 180 degrees is the n of them, summation equal to 180 degrees. Then I propose the following inequality. The square is bigger than that, the right-hand side. So you can view this as an n-dimensional generalization of arithmetic and geometric inequality. It has the freedom of that you just have a lot of free to choose alpha I. As long as the sum of alpha I equal to 180 degrees, the inequality is true. It doesn't matter each particular alpha I exceed 180 degree or even negative, or that doesn't matter. This inequality is true. So it's an open question which I can ask you. So can you use Lagrange multiplier? Lagrange method of completing the square to do that? I bet there's a way to do that. I didn't find it. So what I would do is using the same method as this. Okay, so since this time I have n angles putting them together, but since their summation is equal to 180 degrees, I can draw a lot of vectors but I pave them to be a flat angle. And so here we have to use a little bit algebra. So I would say I first use a vector v1, which is a1 length, but the direction is horizontal to the right. And then each vk, I basically, as I said, I rotate by angle alpha I, keep rotating to keep alpha I. So I will define vk, their coordinates are showed here. And then we will see that their inner product or dot product is equal to ai cosine theta. Okay, so if you are not familiar with dot product, which you can, the so-called dot product is the same as law of cosine. So you can reprove this by using law of cosine. Anyway, so what I want to prove is that this guy would be equal to each pi plus 1 plus qi plus 1. That's what I want to say. And suppose this is pk, qk. Okay, you can use law of cosine to prove them directly. And again, so if you substitute everything into the original inequality, number 1, trigonometry goes away, cosine goes away. And then number 2, you can separate this into 2 pieces, 2 inequalities as before. But this time, even after the separation, the inequality is difficult. And so it's actually, you can do the computation. I don't have time to do the computation here, but then you would see that the inequality is reduced to the same inequality in a special case where all the first n minus 1 angle is 0 and the last one is equal to 180 degrees. Namely, what I claim is that if you are able to prove this inequality, which is much cleaner than the inequality here, which packed with a lot of cosine angles. If you can prove this inequality, then using this machinery, you prove the original more general inequality. But this inequality itself is not easy to prove. How to prove it? Okay, it's not easy because you can imagine it attached to some secant pi over n, which we don't know what it is. When n is equal to 3, I know it's 2. So that's why in the Erdos model inequality where n is equal to 3, you have the coefficient 2. When n is equal to 2, well, you have infinity. N equal to 2 is cosine. Yeah, so we're not talking about the n equal to 2 case. So it has to be at least n equals 3. N equals 4, you get square root 2. But for n equal to 300, obviously you cannot figure out the exact number. It's just a trigonometric constant. How to prove it? Well, it is surprising that we can completing this square by using the Lagrange method of completing the square. So I claim you have this inequality. Okay, of course, it's your first reactions. What? How did you come up with this inequality? Okay, I don't know. I probably can tell you how to come up with such a inequality using linear algebra, but I don't know how at the first place I can as a good way to see why something can guide me to this identity. But it's also interesting to verify this identity. Okay, so how to verify this identity? It requires a lot of trigonometry, which I'm going to actually show you. I'm going to leave one page blank to show you. This is a algebraic inequality by itself, coupled with trigonometry. How to prove it once you are given, okay? So what I'm going to do is I'm going to rewrite things a little bit. I will take omega to be pi over n. That will simplify my computation. So this is the right-hand side. So the right-hand side then would be equal to sigma I from 1 through n minus 2 to sine I omega sine I plus 1 omega, and AI sine I plus 1 omega minus AI plus 1 sine I omega plus AN sine omega square. Okay, what I'm going to do, of course, is prove from right to left. And in order to do that, I expand the right-hand side, and I write this as sigma I from 1 through n minus 2 to sine I omega sine I plus 1 omega 1. And you can expect that if you expand this, you have 6 terms. So let's do this one by one. AI sine square I plus 1 omega plus AI plus 1 square sine square I omega plus AN square sine square omega, right? And the minus 2AI plus 1 sine I plus 1 omega sine I omega minus plus 2AI AN sine omega sine I plus 1 omega. Am I right? Yes. And the minus 2AI plus 1 AN sine I omega sine omega. Okay, so don't just let's make some achievement to begin with. All right, so let's first don't take a look of d squared, d squared. So I will expect that the summation of these two, couple of this, would be equal to that one. Okay, so let's not touch that. Let's study the simplest case, that this term would be my favorite term. This would be the term that is somehow will be, I hope it will be related to that. And let's see. So the nice part is that this guy is going to be canceled with the denominator. So this term is really, let me call this term 1. Okay, so term 1 is actually equal to sigma I from 1 through n minus 2. So the coefficients canceled. It's negative ai plus 1. There's no 2 here. So there's a negative. It doesn't matter if you move. Yeah, so, right. So if you move this to the right-hand side, you would get minus. Anyway, so this is what the yeah, so you may miss one term. So that's number 1 term. Very good, number 1. And so let's see. I hope these two terms, let's do these two together. So let's call this second term. And let's call this third term. Okay, so we already fixed the first term, and let's do the second term. The second term is more complicated. 2 and 2 are canceled. I plus 1 canceled, but there's an I omega you cannot cancel. There's a sine omega upstairs, so this is equal to the sigma I from 1 to n minus 2. Downstairs there's sine I omega. Upstairs there's sine omega. And so you have AI, AN. So that's what you have. Okay, and it looks like you cannot simplify them very easily, so leave as it is for the moment. That's what you have. And let's take number 3. Number 3 is similar, but then it's negative sigma I from 1 through n minus 2. And this time, downstairs sine omega is cancelled. You are left with sine omega plus 1 sine I plus 1 omega sine omega. So AI plus 1 AN. Okay, so this is very nice. And you would see that this summation is, that one is from I plus 1, and I is from 1. So if I is from 1, you can change this to be, because I from 1, this summation is from 2. So why not just say I from 2 to n minus 2, and the sine omega over sine I omega, and the AI AN. I can do that. But then the nice part of this is that you have cancellations. So 2 plus 3. So the first, this is from I from 1 to n plus 1. This is I from 2 to n plus 2. So then you have only one term left. That's the first term. The first term is I from is equal to 1, so they cancels out. So you can actually, this is equal to AI, A1, AN. Okay, so you are done here. So you basically, so fixed with, I maybe this should be equal to n minus 1, I forgot. So you fix that part. All right, so, right, so this, then this is I1, and you will see this summation is from 1, and this is A1 with the opposite number for that. Maybe I wrote it wrong. It's n plus 2 to n minus 1. Okay, so now let's fix these terms. So these 3 terms, let's call this to be equal to number 4, and this is number 5, and this is number 6. Number 6 looks simple. It's just a lot of trigonometric identities you probably have to cope with. But 4 and 5, you probably expect some cancellation, and this is indeed the case. So maybe we can put 4 and 5 together. So let me do 4 plus 5 is equal to, so let's work on 4. Sigma I from 1 through n minus 1. You have cancellations. I plus 1 cancels, so you're left 1. So downstairs is I omega. Upstairs, I plus 1 omega. Right? And then you have AI squared. So that's for the number 4. And number 5 is the opposite. Sine I omega on top, sine I plus 1 omega on bottom, but then you have AI plus 1 squared. Okay, very good. And so this time you need to shift the sigma notation. But what you really want to shift is according to this term. This is I plus 1. You want to make it AI so that you can cancel with the AI before. So let's do it. So we have sigma I from 1 through n minus 1, sine I plus 1 omega, 2 sine I omega AI squared. And here, if you want to make I from I plus 1 to I, so then I is from 2. You make I from 2, right? Because I from 1, this is 2. If from I from 2, then this is AI squared. But then this will be sine I omega because I plus 1 becomes I. So sine I omega becomes I minus 1 omega. Okay, so very good. So you compare these two, you will see that you first assume that, so there's one extra term here. This is n minus 1. So this is n minus 1. So I from 1 should be separately considered. So it's I from 1 is 2 sine omega sine 2 omega. Okay, AI squared. That's leave separated. And then you will see that you basically have sine I plus 1 omega time plus sine I minus 1 omega. But let's write a separate identity here. Sine I plus 1 omega plus sine I minus 1 omega is, you expand it, you get sine I omega cosine omega plus cosine I omega sine omega. And the second term is sine I omega cosine omega minus cosine I omega sine omega. So these, the two terms, second term will cancel, and the first term will make it 2. And so then downstairs there's sine omega that cancels out. So it's basically I from 2 to n minus 1. And so this would be equal to sine. Okay. I am sorry. There was a there was no there. There was sine omega, and so AI squared, which sorry, cosine omega, because cosine omega. That's the point. Cosine omega, but cosine omega is exactly, this is cosine omega. So in front of the coefficients. That's true, but there's an exception. This is also cosine omega because this is 2 sine omega cosine omega cancel with downstairs cosine omega. So this is I from 1 through n minus 1, and we have the last term for I equals n. That would become from this guy and the summation here. So let's do the last computation. Basically, I want to prove an identity, sigma I from 1 through n minus 1, and 1 over 2 sine I omega sine I plus 1 omega sine square omega. Will this be equal to 1? So that's the question. Let me write it more carefully. So sigma I from 1 through n minus 1, 2 sine I omega sine I plus 1 omega sine square omega. I claim that this has to be equal to, maybe equal to cosine omega. That has to be equal to that. So how to prove this? How to prove this inequality? I would use something like I forgot the method. You basically write this as the so I will write this as sine I omega minus sine I plus 1 omega. Let's try this. This you will produce I omega minus sine I plus 1 omega down multiple downstairs, but upstairs I plus 1 omega minus sine I omega. But then this would be equal to subtraction. I forgot. Okay, I forgot this the last trick. I suddenly forgot how to prove it. Is there anything I computed wrong? I didn't do anything wrong. So this has to be equal to I guess I can use cosine. Okay, maybe I can use cosine omega I omega. Okay, cosine I plus 1 omega. So then sine, okay, I think I got it. So basically this would, I can consider tangent, cotangent, I omega minus cotangent, I plus 1 omega. So it's cosine I omega over sine I omega minus cosine I plus 1 omega over sine I plus 1 omega, right? And so this is sine I omega sine I plus 1 sine omega cosine, let me write in the nice way, sine I plus 1 omega cosine I omega minus cosine I plus 1 omega sine I omega. However, so this is exactly equal to sine omega, because sine omega is sine I plus 1 omega minus I omega. So that's what you get. Okay, so sine I omega sine I plus 1 omega. So now we are done, because essentially I write this in terms of subtraction of 2, and if I do summation, they cancels out, right? So I'm not going to do the detailed computation, so I probably can. Let me do it. So this is 1/2. You factor out another sine omega, sigma I from 1 through n minus 1, cotangent I omega minus cotangent I plus 1 omega. And so only survival term will be the first term, and last term is half of sine omega cotangent omega minus cotangent, the last one will be cotangent n omega, if I'm not wrong. Yeah, so cotangent m omega would be equal to, because omega is pi over n, so cotangent pi, that's, cotangent pi does not exist. I maybe something computed wrong, but that's the spirit. So maybe I skipped here. So later I will write a more clean solution to that in the homework. All right, so for the detailed proof test, here is the one. All right, so I think we're pretty much past 1 hour, but I still want to show you some of my findings. Okay, so these are completely new. So the question is why we want to restrict ourselves to the case that alpha plus beta plus gamma to be 180 degrees. How about alpha plus beta plus gamma is equal to 90 degrees? Okay, so this is the inequality I obtained. So in this case, the optimal number would be 2 over square root 3. And here is my inequality. So remember that the coefficient is different from 2, which we talked about before. This is because alpha plus beta plus gamma is equal to 90 degrees. Okay, so now let's see, we use the same trick, but this time since the summation is equal to 90 degrees, so I can still use the trick I mentioned before. And so then the inequality becomes this inequality. This inequality is actually more complicated than the previous one. The reason is that you cannot separate this inequality into two parts. So in the previous case, let's compare with how to copy from the previous one. In the previous one, you see a to z, z to y, y to a. So these two terms are basically separated. But here, you cannot separate them. So it's basically a to y1, y1 to z. Okay, z, of course. So from z1 to y, y to a to z2 to y2. It goes through just the one chain that goes through all the numbers. So it's more difficult. But fortunately, this is not hard if we just do it. Not hard in the sense that the n is only equal to 3. So we can do this by brute force. So what do we mean by brute force? So what I can do is I can look at it and see that this inequality is true, is a quadratic inequality for, like, say, y as for z, right? For z1. So sorry, this is a c1 here for z1. And so this inequality is true for any z1. So we can take one z1 to be, so minimize it. So that means if I take a z1 to be 2 over square root 3 y1, and then we can reduce this inequality into the following. So z equals, actually, this is z1 squared minus 2 over square root 3 y1 z1, this quadratic inequality for z. So this quadratic is minimum when z is equal to 1 over square root 1 3 y1. So if you can prove this minimal case for any other z, that the inequality should be true. And so z is equal to that. I put it in. I will get a squared plus y1 squared plus y2 squared. Z1 is 1/3 of y1 squared plus z2 squared, which is bigger than 2 over square root 3, a y1, y2 z2 plus z2a. And this y1, z1, if you put them together with the coefficient, you would basically get 2/3 of y1 squared. Okay, and you go to the right hand side, minus y1 squared. And if you do the computation, this is negative, but then this is y, so you get a squared 1/3 of y1 squared plus y2 squared plus z2 squared, which is bigger than 2 over square root 3 a y1 plus y2 z2 plus z2a. So that's the inequality you want to prove. And so from this one, you see that y1, you can optimize y1 because there's only y1. Y1 goes to a to z to z2 to y2. So the optimal case for y1 is y1 to be equal to, so this time you have to do some computation. 1/3 of y1 squared minus 2a square root 3 y1. So y1 is 2/3 a over square root 3. That's the optimal one. So you make upside down. It's 2 square root 3a. Am I right? So y1 is that you put it in. Each time you can reduce the order by 1, and you can keep going. Keep doing so. Eventually, you would get the correct answer. okay? And the optimal one is this. All right, so let's say I have a Wenzenberg formula in triangle geometry. So let ABC be the triangle, and so a squared plus b squared plus c squared is bigger than 4 times square root 3 times the area of that triangle. That's called the Wenzenberg inequality. And how to prove it? So now I can do it because if I have a triangle, 3 sides are A, B, C, so I will take alpha to be pi minus A, beta to be pi minus B, and the gamma to be half of pi minus C. So then alpha plus beta plus gamma, well, equal to 90 degrees. And then I can use the inequality a squared plus b squared plus c squared is bigger than 2ab cosine alpha plus 2bc cosine beta. It doesn't matter. Oh, it does. So ab cosine gamma, 2bc cosine alpha, 2ca cosine beta. But remember, right, alpha and A are complement, beta and B are complement, so these are 2ab cosine, sine C. Sine C. Square root 3, right? This is the coefficient. Plus 2 over square root 3 BC cosine A plus 2 over square root 3 CA sine A sine B. So I keep making mistake. Sine A, and here CA sine B. Very good. So remember the formula for triangle area, half of AB sine C is the area. So then you have 4 square root 3 triangle area, 4 square root 3 triangle area, 4 square root 3 triangle area. That's 4 square root 3 triangle area. So that proves the Wenzenberg formula. Okay, I will stop here, or maybe I can give you the question or conjecture. So what is the optimal number such that a1 squared, an squared bigger than this optimal number, let's call it Cosine, a1, a2 cosine alpha 1, an minus 1 an cosine alpha n minus 1, an a1 cosine alpha n. Okay, we know that if n equal to 3, then Cosine is 2 over square root 3. But what are the others? So that's the question. Thank you very much.